Hello everyone, my report is all about floating point addition algorithm. Okay, let's have a quick recap of what floating point numbers are. First is why floating point numbers are actually needed. First is limited computer memory, and you cannot store numbers with infinite precision. Example, you cannot store recurring results. 10 divided by 3 is equals to 3.3333 to infinity. And the most important is the speed and efficiency. For example, if I were to multiply 30,000,000 by 0.00000015, it will take you a long time to do that. Rather than using the floating point numbers, you can easily multiply the numbers. For example, in this significant format, you can easily determine how to multiply the values actually. How do floating point numbers work? The idea is to compose a number of three main parts. First is the sign, which is positive or negative, a significand that contains the number's digits, and an exponent that says where the decimal or binary point is placed relative to the beginning of the significand. Negative exponents represents numbers that are very small, example close to 0. Such a format satisfies all the requirements. It can represent numbers at widely different magnitudes, limited by the length of the exponent. It provides the same relative accuracy of all magnitudes, limited also by the length of the significand. It allows calculations across magnitudes, multiplying a very large and a very small number preserves the accuracy of both in the result. Decimal floating numbers usually take the form of scientific notation, with an explicit point always between first and second digits. The exponent is either written explicitly, including the base, or an e is used to separate it from the significand. Okay, let's have an example. With a significand of 1.5 and exponent of 4, the scientific notation of this number is equals to 1.5 by 10 raised to 4, which has a fixed point value of 15,000. The next is the negative 2.001 with an exponent of 2, which has a scientific format of negative 2.001 by 2 raised to 2, and which has a fixed point value of negative 200.1. The next is 5 with an exponent of 3, negative 3, which has scientific notation of 5 by 10 raised to 3. And converting it to fixed point values will be equal to 0.005. And lastly, 6.667 with an exponent of negative 11 and then a scientific notation of 6.667e raised to negative 11 with a fixed point value equals to 0.00000006667. Okay, let's come now to the standard floating point number. Nearly all hardware and programming languages use floating point numbers in the same binary formats, which are defined in the IEEE 754 standard. The usual formats are 32 or 64 bits in total length, in which the singular precision format contains of 32 total bits and a significant bits of 23 plus the sign, exponent bits which is 8, smallest number can be 1.2 by 10 raised to 38, And the largest number is equals to 3.4 by 10 raised to 38. In most computer systems nowadays use double precision, which is equals to the 64-bit, and a significant bits of 52 plus 1, which is the sign, exponent bits, which is 11, which has the smallest number of 2.2 by 10 raised to 308, and the largest number, which equals to 1.8 by 10 raised to 308. Okay, the standard floating point number. Note that there are actually some peculiarities. The actual bit sequence is the sign bit first, followed by the exponent and the significant bits. The exponent does not have a sign. Instead, an exponent bias is subtracted from it. 127 for single and 1023 for double precision. This and the bit sequence allows floating point numbers to be compared and sorted correctly, even when interpreted them as integers. The most significant digit is omitted and assumed to be 1, except for subnormal numbers which are marked by an odd exponent and allow a number range beyond the smallest number given in the table above, at the cost of precision. There are separate positive and negative values, differing in the sign bit, where all other bits are 0. This must be considered equal, even though their bit patterns are different. There are special positive and negative infinity values, where the exponent is all 1, and the significand is all 0 bits. There are the results of calculations where the positive range of the exponent is exceeded, or division of a regular number by 0. There is special not number or none, which is commonly in JavaScript. Values where the exponent is all 1 bits and the significand is not all 0 bits. This represents the result of various undefined calculations, like multiplying 0 and infinity, and any calculations involving a non-value, or application-specific cases. Even bit-identical non-values must not be considered equal. Okay, let's now come to the ALU floating point addition. We have steps to add two floating point numbers. The first is compare the magnitudes of these two exponents. Number 2 is make suitable alignment to the number with smaller magnitude. Number 3, perform the actual addition. And number 4, perform normalization by shifting the resulting mantissa and adjusting the resulting exponent. Okay, let's add sample numbers in here. The first is to add 10.5 to 0.25. Okay, the first step is to convert the decimal to binary, which is equals to 10.5 is equals to 1.1010.1, and 0.25 is equals to 0.01. The next step is to normalize the results. 1010.1 is equals to 1.0101100 by 2 raised to 4. And 0.01 is equals to 0.1000000 by 2 raised to negative 1. Then you have to make the exponents the same. You have to move the decimal to the left. So we have the result of 0.0000010 by 2 raised to 4. Now you can add the matrices together. 0 plus 0 is equals to 0. 1 plus 0 is equals to 1. 0 plus 1 is equals to 1. 0 plus 0 is equals to 0. 0 plus 1 equals to 1. 0 plus 0 is equals to 0. 0 plus 1 equals to 1. And 0 plus 0 equals to 0. And the last step is to normalize the result. As you can see, the results are already normalized. And we have the result of 0.10101100100. Now we can double check if the result is correct. In decimal, if you add 10.5 plus 0.25, it will be equals to 10.75. And convert it to binary, 10.75 is equals to 1010.11. Normalizing the results will give us 0.101011